Aly El-Kadi is a professor of hydrology, Department of Earth Sciences, and a researcher at the Water Resources Research Center, PhD, from Cornell University. His research deals with assessing effects of climate change and land use practices on aquifer sustainability, watershed assessment and modeling, application and assessment of various types of groundwater models, and contamination by cesspool sources and arsenic. He's currently leading the modeling team in EQI and serving in the leadership committee.
Okay, good afternoon, everyone. Welcome to the seminar. Here's the title of my talk. It's about hydrological modeling, challenges in Hawaii and the Pacific. Okay, I'd like first to acknowledge the support I had over the years from students, graduate and undergraduates, as well as researchers and my fellow faculty members, especially students who have done a great job over the years. I'd like to especially acknowledge the high productivity of a number of them, including Bob Whittier, Collier Rotzel, and Chris Scholler. I'd like also to acknowledge the support of the funding agencies here in alphabetical order: the Board of Water Supply, the Hawaii Department of Health, EBSCOR through EQI, Pacific RISA, and the USGS. Okay, here is the outline of my talk. We'll talk a little bit about history, then talk about advances in desktop modeling, then talk about the modeling process and the challenges associated with it, then highlights of some sample of my studies, and end up with update of EQI research. Okay, so go back to a little bit of history. I'm sure some of you remember this one. For the young generation, this is called punching cards, and we used to use this for writing software. So for example, if I have a short program like this, assemble and calculate the area of a circle. So here is I will read the radius of the circle, and here I calculate the area, then print the results. So this is 9 lines program, so I will require 9 cards like this. Then here is the machine that we use to punch in the cards, and it is like a typewriter, right? Typewriter kind. Then here is the cards, and you do it one by one. And basically, I used to go at night so I can find room to type in my cards. This would be a typical deck of cards for one specific software. And I assume this marker line here is intended in case you drop the deck, so you can at least get some idea about the order to sort them back in the correct order. And you should have plenty of these and make the arrow strong enough to keep this deck in order. Okay, so here is you hand it over to the formally dressed program or computer operators, then they feed it to the card readers, then you hope they will not stuck or something wrong that we'll have to feed it again. Then in the next day you found your results wrapped on your hard copy, and now in case you are moving after your studies, this is, I assume, after 4 years of graduate studies, including classes and research, this is how you'll be carrying your software. And I assume one of these could have done it for us. Okay, now go to present. Just fast forward to what we have now. So this is like a site on the Big Island. It's called Keahu Basal Aquifer Model here in the side of the island. I can use very quickly in my desktop the software to create a 3-dimensional view of the site. Then if I'm using this in numerical analysis, like say using the finite element method, so this would be a number of elements, and I can go for very high resolution, like for 3-dimensional mesh, 25 layers. I needed, or I can design for more than 1.8 million elements, these little things here, and 1 million nodes, which are the points at the corner of the triangles. And I can go sizes down to 2 meters. And if you're familiar with the numerical method, this is how number of equations that you need. So I need to solve 1 million simultaneous equations, and they can be nonlinear if you're dealing, for example, with um, density dependent flow. They can, take time, but they're still possible to do on your desktop. Something we could have never done years ago. And this is a screen, how it looks like for some software. It's called the FeeFlow. And this is your results screen. So I have a three-dimensional view that shows the extent of the saltwater lens or the saltwater distribution in the aquifer. And this is the cross sections. And this is plan view. I can show the salinity profile at different levels. So all the data I have, all the results can be manipulated from here. I can just basically select what I want to display, and I can communicate with maps. So if you click over this tab here, you can see all kind of maps that you can import to the system, like GIS maps, where you can read the data and integrate it relatively easily in your model. Then here is what is good about it is that you can monitor everything live. Like here, I can look at the salinity, I can look at the hydraulic head, I can look at the pressure, I can make cross section. This is all while the program is running. I don't need to stop it. I can also look at the size of the time step for simulations. I can adjust if I have trouble or problem. I don't need to stop the program. Sometimes I can pause it or just make changes, or I can save the results at certain times and I can recall it anytime. So if it crashes, I can go back and restart. So you don't have to lose what you're doing. A nice also feature, I can look at the water budget dynamically all the time and see if the model is behaving correctly. If not, I can stop it, obviously. So I don't have to wait hours and days and restart. This is an example of a model for the whole island of Oahu. This is relatively coarse, about 500,000 mesh elements. And this is how they look like. This is like 40 vertical layers. And this is a close-up to the finite elements. And here's quickly the results. I can look at simulated salinity at different depths. So this is basically close to the surface. So we have fresh, which is here is a purple color, and the blue is fresh. And as I go deeper, so we can get into higher salinity and higher until you get to the salt water. So exactly what is the modeling process? The first step is to create a conceptual model of the site that includes all the site information, geological and hydrological features, and decide what processes you would like to simulate. Usually we would simulate water flow and contamination. Then after that, you create a numerical model that will simulate the processes, which are the water flow and contamination here. Then I can solve for that, for the hydraulic head of the water level or chemical concentration. And I can simulate also density, various fluxes at various locations and times. Then after you create the model, you do some validation or calibration validation. You gain confidence in the model. Then after that, apply the model. We can apply it for understanding processes, designing field work, and predictions. That's something good about models. You don't have to wait for site for years. You can study it in your comfortable office. You can do simulations for thousands of years and do some scenarios if needed. So some important issues, as I showed before, the model area is divided to small elements or cells, and the solution obtained at the nodes. The solution requires solving a large number of equations, as I mentioned before. And I need something important here is calibration, just to estimate aquifer parameters that can give me the results at known points or locations. So you change the parameters by iterative process to find out the parameters that will match field data with your results. And validation is similar to calibration, but you don't have to change the parameters. So once you get the parameters from calibration, you just apply it here and see how accurate the model is. Okay, and once you calibrate and validate, the model is ready for use. Calibration is a very tedious process. It can be done manually or through automatic process. So manual means you do guesses at the beginning and update or change until you get the match. The computer more systematically do it for you through many iterations, and it's basically the same process. Start with guesses, then adjust until you get the good match. And it is a very tedious process, as I mentioned, and there is important issues of uniqueness. Like if you calibrate the model for a certain time, would it be applicable to other times? And also, different combination of parameters can give you the same answer. So, aquifer should be unique, but it's not exactly that through modeling. So the many challenges has to do with creating conceptual model, which reflects our understanding of what is happening. Then if the model is high resolution, it will take large computer time. Then we don't have enough information for model calibration and validation. And this is something important in Hawaii, where we have really serious issues about data availability. And as I say, garbage in, garbage out, unless you really calibrate the model accurately, unless you have enough data to do that, then it will be, results will be questionable. So we have the reasons for challenges in Hawaii. The climate is very complicated. Simply, you need high resolution climate information. Data in one watershed are not applicable or can be used for a neighboring watershed. The climate or weather is variable, highly variable in times and space. So that's affected really on our ability to do predictions. Hydrogeology, as you can see here, this is dikes, sedimentary formations, basalt. They all of high variability. And even there is questions about, validity of these porous media models for things like that. Even within basalt, there is different layering of different properties. As you could see here, aquifer or ground surface are very steep. And this area is very difficult to access, and there is no data available here. So hydrogeology is very complicated by the lack of data and the suitability of models to deal with that. For example, models for sediment cannot work for highly steep area like this. The limits are like 25%, while we have 100% slope. So here is some of the studies we have done over the years, and the objective could be addressing actual problems, water problems, such as nitrate contaminations, flooding, landslides, on-site disposal systems, surface water harvesting, watershed and climate change, and dealing with specific issues in the Big Island through EQI studies dealing with water availability and understanding of the systems. Then also we did some studies to meet government requirements, such as designing protection plans for watershed and assessing water protection areas. We did some sustainability studies in Korea, Jeju Island, and in American Samoa. There is others which is not falling within these categories, such as bioremediation, aquifer parameter estimations, and local scale geological variability. So I will go through these studies very quickly. Okay, here is number one, is Source Water Assessment Protection Program. And this program was required or mandated by the federal government. And that was required through the Safe Drinking Water Act, which was done in 1996. That included a SWAP, Source Water Assessment Protection Program, SWAP, mandate. And this required every state to conduct assessment of public drinking surface and subsurface water sources. They can be wells, subsurface, or surface such as intakes on lakes and reservoirs. And the process includes delineating the protection areas, like say around the well, and assess potential contamination activities, identify all potential sources. Could be actual or existing sources if they have the potential to leak, such as gas stations, factories, military bases, agriculture, etc. Then estimate the risk for each source to identify the relative risk, high risk, low risk for each individual source. Here is the result. So we can see here, this is for the island of Oahu. Each well is a small circle there. Then we use the travel time criteria. And the blue reflects two-year travel time. So any chemical would reach the well within 2 years if it is within the blue area here. The red is for 10 years. It will reach the well in less than 10 years within the red. So this is how the water source is protected. So we have enough warning time and can do something about it. Then the risk is given by the color of the wells. Red, high risk. Blue or green is less risk. And here is the relative values for that. So you can identify the risk and basically see in your planning. That's important to know. So the objective was just to predict these maps, okay, to create these maps. But actual protection is not. Like, for example, I know there are sources of contamination, but I cannot do anything about it. But the county of Maui actually used our results for permitting. So like if you want to have, build a gas station within the area, they would say no, because this is not allowed. The second project here has to do with risk assessment of shallow landslide. What we did was to use a model called Stability Index Mapping, or abbreviated as SINMAP, combined with hydrological information to create these maps here. So that would include rainfall or weather information. That will include the land cover and the soil type and slope. And what we found out was to identify the zones of higher risk, defined here as the green, and I don't know why they call it defended, and less risk as we go down here until it is stable. And we tested the validity of results compared with actual landslides. And these are the squares here, the white squares, and you see the model is reasonable. Most of the actual landslide falling within the green or red, some the yellow here. So that map is useful, I guess, if you're buying a house, that can be useful for your decision making. Number 3, on-site waste disposal risk assessment. And here is a map for the island of Kauai. And actually, you can see here the density of the septic systems, which are on-site disposal system, or OSDS. And unfortunately, the high density is falling across or near the shoreline. So you can imagine, for sea level rise, that would be a very serious problem because of this. And we have really to worry about disposal because we have more than 100,000 units in Hawaii, and that release 70 million gallons a day of minimally treated wastewater, and that can end up in the ocean. And inland, it can increase nitrate concentration beyond the acceptable limit. The next one is about Heeia watershed in Oahu, related to climate change and the water budget. So here is the climate change maps, and we use the statistically downscaled rainfall calculations, and the map shows the anomalies, and yellow and red are decrease in rainfall, meaning area gets drier, and green and blue is meaning increase or getting wetter. So we can see the leeward sides getting drier and the windward side getting wetter. And we used two scenarios, one called RCB 4.5, which is a representative concentration pathway, meaning higher green gases concentration, and the 8.5, which is even higher than 4.5. So these are for the wet seasons, and these are for the dry season. And we can see, as I mentioned, the wet region gets wetter, the dry season gets drier, and basically Maui County looks not so good, it's worse, getting much drier. And Oahu has so much changing between drier and wet seasons. So what was the objective of the Heeia study? It basically using the statistical downscaling results to calculate the water budget, meaning estimate surface runoff, groundwater recharge, evapotranspiration, interflow, base flow, and stream flow. So water falls on the ground, will evapotranspirate, and basically that's elements reflect surface runoff, groundwater recharge, which is important to assess groundwater sources, and interflow, base flow, and end up in the streams as a stream flow. So here is an example of the results. So here is the change in rainfall, wetter, drier. Then based on the changes, we can see how surface runoff will change. Again, this is increase in surface runoff, and here is decrease in surface runoff. Same for lateral flow, which is flow from the ground above the water table. And this is the total stream flow. Here is the base flow, which is the flow below the water table. This is actual evapotranspiration, and this is potential evapotranspiration, the recharge. And we consider different cases, like here, rainfall change only, rainfall and temperature change, and rainfall temperature and CO2 changes. It's more realistic to consider all the three variables because there is intercorrelation or cross-correlation between them. So this is good for planning and management resources. For example, you can address flooding here, you can access for recharge, future needs for drying conditions, for example, or the potential basically shortages. For American Samoa, we did a number of studies, including installing a monitoring station for weather and for stream flows. Then did some modeling and assess contamination to wells and find out which sources of contamination are more serious. Then did some collaborative modeling with the agencies there. Here is some examples. It was to study flooding in the Paga'alu watershed. which is shown in green here over in Tutuila Island. And the objective was to study how climate change can affect the stream flow. So the red here shows you the median value for baseline, which is the current. Then the blue is the predicted based on climate change. And this is for RCP 4.5. Here is the same results for RCP for 8.5. The conclusion is that with peaks, it's getting higher, and the hydrograph is getting soon, closer or moving, shifting to the left, meaning flooding could be happening sooner. These are two sites on Fagara. Then here is the flooding. So we estimated flooding at the lower reach of the Fagala stream. And you can see this is actual storm that happened in 2014. And based on our simulations, the peak of the flood was at 2.4 meters. Then we did simulations for 50-year flood and 100-year flood. The brown here is the actual storm. The blue and red are the simulations. You can see the peaks are almost the same. The areas are identical except of some, more areas covered by the flooding. But so we believe actually this was very big storm, close to 100-year flood storm. Then another study on American Samoa had to do with assessing sources of contamination or relative sources of contamination based on different sources. So American Samoa, Tutuila have septic systems, they have agriculture, they have piggeries, and there is also natural contamination likely from the conservation lands. So we found out that OSDS septic system have the highest risk, that's the blue color, followed by piggeries, then agriculture, and finally natural contamination. Why is this important? Because you can, if you want to reduce the contamination, you start by attacking the highest risk, which is from septic system, as we can see here. This maps here shows the distribution of contaminants because each or caused by each, like piggeries here, OSDS, septic systems, agriculture, and nature. Number 6 is reservoir water harvesting, which is a project funded by the Board of Water Supply, Honolulu Board of Water Supply. And the idea is to collect water from reservoir, surface water, and inject it into the subsurface. The advantage is that we reduce evaporation from the surface water and reduce the chance of contamination, surface contamination. And also, it is consistent with the climate change because you are collecting from wet areas to dry areas and use it in the dry areas. So here is the study sites. This is Kalihi and Noano aquifers, and this is Noano number 4, where surface water will be harvested and injected in this area near Noano number 1. So the objective was to see if it is feasible to collect water and to study how the aquifers respond to that. To study the amount to be collected or harvested, we used a model here for the reservoir. And we can basically design the operation mechanism. So we have the water, if it goes above certain level, go to the spillway. We have gates that can open by different openings to collect surface water. And we have to provide spacing for flood control and use waterfall supplies and protection, recreation, and power. So the idea was to optimize how much you can collect without violation of any of these constraints here. And we can see also the effect of climate change on these processes. So here is the results. So we have 33 years of data between 1982 and 2014. So we use the models to do these different scenarios and estimate that we can collect more than 1 million gallons a day for most of these 33 years, except 448 days, which is amount to 3.7%. That's if we have the gates fully open. If you open the gates at only 40%, it is better option. We only miss 2.3% of this 33 years. That's 274. If we want to collect about more than 2 million gallons a day, this is respective numbers. So we lose like 11% of the days and 8%. And if we open the gates, here is fully open, and here is 40% open. For climate change, we have the option for 40% open, and you lose, higher number of days for more than 1 million gallons a day, and for more than 2 million gallons a day here. Obviously, with climate change, we miss more days. So basically, and very quickly, we can collect between 1 and 2 million gallons a day with reasonable strategy here. So that was the surface water phase. The injection phase, we did some electrical survey, thanks to Henrietta, who helped with that. So we did 4 surveys, 2 along the highway. This is basically poly highway, and another shorter survey, same location, to get higher resolution. Then 1 survey across like this. The idea was to try to use electric resistivity to find the sub-geology, and we identified alluvium, Honolulu volcanics, Ko'olau basalt as of main formation, and through comparison with a nearby borehole log, we identified this as a distribution for the site. So this is idealized cross-section like this. And unfortunately, we have to inject above the water table, which is the white line here, which would be done in the Honolulu volcanics, because we cannot really inject below the water. It should be nicer to inject in the basalt, but this is not been allowed because of the Department of Health regulations. So the idea was to simulate the injection process to make sure that we can, have enough room not to connect to the water table or flood the ground. And here is the results. This is after 10 years, and this is after 25 years. We can see still okay, but it is very close to being connected with subsurface, with the saturated zone at the water table. So we recommended to either reduce the injection or distribute over a number of wells over the area. And the good news is actually the Board for the Supply is planning to do the project, and they started already the engineering approach. The next one is the local scale geological variability, which was done with one of the REU students, which is just in the past summer. So let us say this is just basalt formation, which is number of flows, and that can range by clinker zones, which are highly conductive, and flows and bohoi. So this is basically the real life, and we can digitize it like this. And you can see the fractures here, and thanks to Scott who made this maps and digitized for us. So this is the real life, and this is our conceptual model of that real life. So water can move faster in the fractures, and basically it could be also flowing between the fractures in the matrix. So the objective was, if we can approximate this as real life, can we further approximate this as porous material? So basically no fractures, this is all porous material, and of different conductivities, or we call it effective conductivities. And even if we can go further and use only one material rather than 1, 2, 3 materials here. And the arrows give you the conductivities and the vertical and horizontal that can be different, what we call it anisotropic feature. So this is heterogeneous. This is homogeneous, meaning it's the same conductivity everywhere, but it can change between vertical and horizontal. So again, the objective is we can replace this real system with this approximate system, or by using effective conductivity. So here it is, validity of the equivalent milieu approach, which is replace the fractures system with the porous material system. So first, we simulate the fracture porous media for water flow and transport. Second, calibrate equivalent system by trying to match whatever result we get from here, and assess the likely error or expected error, because you don't expect the equivalence to be 100% correct. And here is monitoring points. So we try to match our simulations at all of these points. So here are the results. So here's the hydraulic head at different locations. And this is the fracture porous system, the real one, and this is the equivalent one. And you can see they match, where is high and where is low is low. This is at certain time. And here's the contamination. So if we have a contaminant moving from the side, we can see the effect of fracture flow. We can see preferential flow, where the contaminant move faster through the fracture, slower within or between. So this is after 1 day, and this is equivalent porous media. We can see the same trend, high is high and low is low, but obviously there is huge errors. For example, here is no contamination, in between the fracture, but actually the model here predicts high concentration. And it can change with time. So this is after 4 days, and for the porous, fracture porous and equivalent one. And we found out the error gets very small and even smaller very quickly as we reach a steady state for hydraulic head. However, the error is significant for contamination. So only after 100 days, the accuracy is accepted. So the conclusion, we can use porous media assumption to model flow, water flow, but we cannot really do it for transport. The last project is the EQI modeling. We've been doing it in West Hawaii. And the objective of EQI is to study the submarine groundwater discharge and how does it impact the coastal ecosystems. Then how could we study, or what is the impact of the rift zones on groundwater flow for the Aly volcanoes area. Then what is the source of water? So basically study the amount and the flow path for water as it goes to the ocean. Then finally how this flows affect the water quality and the specific or yield of aquifers. So just for managing the sources, the resources. So we'll integrate our numerical models with geochemical modeling, such as the bath lines, water budget, and submarine groundwater discharge. So this is done through field data collection, and we use this information to calibrate and validate our models. And for age dating, nutrients like nitrate, silica, and isotope, as well as microbial. So again, all of this information can be very valuable and validated in calibrating and validating our models. Another important way of assisting the modeling process is through geophysical modeling, where we try to build accurate geological model for the aquifer and use this information for, again, for validating, calibrating, validating our models. Once we're done with this, we use the information and the model to do aquifer management to study water quality and quantity issues. So we developed 3 models. One, we call it WHR for West Hawaii Regional Model, covering this large area here, and we have to extend to the ocean. So we can study submarine groundwater discharge. And this is used to answer questions 1, 2, and 3. 1 and 2 has to do, or 1, 2, and 3 that have to do with water flow and submarine groundwater discharge. Then this is covering a smaller area. We call it Keahu Basal Aquifer. And this is used to answer question 1 and 2, water flow and pathways, and Q4, which is the management. Then the cross-section model is used for answer Q, flow, and basically we can integrate it with available information to build basically better model for flow path lines. Then this area is very complex. So this is like the large WHR model. And you can see here the surface geology, 3 volcanoes, very, very complicated. And we don't know really the extent or the distribution of geological at the greater depth. We have rift zones. Some of it are not well defined. We don't know even if how deep that formation is. And we have what we call a barrier, where there is a jump of water level less than 3 meters to much higher, 50 meters or more across from the barrier. The exact reason for the jump is not well known. So here is some of the results. So this is for the West Hawaii Regional Model, the WHR model. And we calibrated the model, tried to predict the measurements for available records. And you see the calibration is very good. And the model was able to identify the need for low conductivity zones. So here is what we call a barrier, but actually the barrier should be extending here. Unfortunately, there is not much data available in the high level area or high elevation area, and you can see uncertainty here, not very high uncertainty in this area. That's why we need more information through geochemical and geophysical research. Then we simulated age, and we found out that based on model calibration, this is the hydroconductivity, which I showed in the previous map. Excuse me. And the model predicted much older water in this area than here. And this is supported by the simulation of travel times. Obviously, this water is older because it samples water as travel long distances here, compared to here, which is the source is much closer, or the baseline are shorter, so ages here should be younger than here. This is all modeling, but to validate or calibrate our model, we did actual field measurements. You can C14, CFCs, and tritium helium. And this is the simulation I showed in the previous screen. Is it reasonably match, the measured C14? We're still doing some work on that, but low or young and old, young and so this is the third or the second model, which is KBA or Keahu Basal Aquifer. And this is a simplified model. We estimate the net flow across the barrier here, and just model the area outlined here. And basically, it's more suitable for managing the resources below the barrier. So we did not simulate the flow here. We just estimated the net flow, and it's a detailed simulations here. And it did the calibration. It matches well, which gives us the distribution of hydroconductivity. Then we can do scenarios. This is the baseline, which is current, and this is, let us say, due to climate change or overuse or things like that, can we see decline for water level? This is water level for the baseline current, and this is under scenario where we had reduction and recharge. There is example for the water budget. We can do different scenarios. Like the blue here reflects the net flow. So here up to minus, this is percentage, like 75% reduction. And we can look at the red, which is the SGD coming into land. So this is from the ocean. We can see, like increase 8%, decrease 11%, etc. Then this is the green is the flow out, like here increase in 27%. And depending on your purpose, you can design or accept the scenario. If you are interested in ecological factors, then scenario 1 would be the best, give you increase in freshwater flow to the ocean. If you are worried about, but in the meantime, you have increase in inland salt water. So basically, based on comparison to the baseline, you can choose whatever scenario is appropriate for your needs. Then the final model has to do with a cross-section across the site here. And the objective was to integrate geophysical work with the 2D modeling, try to build a accurate geological model. So we had some scenarios, like different zones, different conductivity. Then here we have a vertical burial. Then here we have layering or different conductivities. So here is the salinity for the model. So we base this to the Niels group, which will invert it and estimate the MT and using inversion to give you this profile here. So this is one of the examples, and this is the respective MT measurements. And we give them all the hydrological data plus salinity and try to see, based on inversion, if we can invert it back to hydrological data. So for example, inverted MT, then use MT to predict porosity and salinity, and assess how accurate that inversion process is. So in other words, can we use profiles which obtained from MT inversion can be used to complement hydrological investigation, and how the error or uncertainty can be affected by that. So here is the black is mean of porosity based on inversion, and here is median, and the true basically is this line here. So for salinity, this is the true, and the others are the same, mean and median. And we can see, the match is not great, but at least we have good idea, and we can basically see how we can improve on the technique as we go on. Okay, so integrated science is the key. Basically, due to the lack of information, we can integrate geophysical, geochemical with numerical modeling for best, assessment and reduction of uncertainties. And I always tell my students, you are the ones charged. The model can be great, but unless you're really careful, things can go wrong. And okay, thank you very much.